Today we are going to talk about static equilibrium. Static equilibrium refers to the concept that the sum of the forces adds up to zero. When we are talking about forces, forces are vector quantities that have both an x and y component to them. When these forces are added together, multiple forces acting on an object, if they cancel each other out and their sum, also referred to as the resultant, equals zero, then we are in a static scenario. Isaac Newton told us in his first law that an object in motion stays in motion and an object at rest stays in rest unless acted on by an unbalanced external force. Unbalanced meant that the sum of the forces did not add up to zero. Another way to look at Newton's laws is that Newton's first law is to say that when there is a balanced force, that the sum of the forces equals zero, that an object will keep doing what it is doing. So an object in motion stays in motion and an object at rest stays at rest. In this particular lab activity, what we're going to do here is we are going to demonstrate how force distribution occurs when applied through multiple directions. So we're going to have multiple force vectors in this particular demonstration. At the end, I'm going to have you do some calculations related to this concept. So I have here a force sensor. These are these blue objects located on each side of me. And I have a mass. This mass, when we put it on the balance, we find that it is a 1,000 gram, 1 kilogram mass. And because we know that the weight of an object here is equal to mass times 9.8, mass times gravity, then we know that this is a 9.8 Newton object. This string is going to be hung on a force sensor, and this string is then going to hold this mass. On the screen, you can see the force sensors are not balanced and not tared to zero. So I'm going to tare it. The force sensor that is on my left is on the top. The force sensor that's on my right is on the bottom. When I take this 1 kilogram mass and I hang it here on this force sensor, the force sensor reads 9.8 newtons, which is exactly what we would have predicted it would read. When I take this and I move it over to the other side and I, again, tare it, you can see it's now zero. I attach the weight, and again, I read negative 9.8 newtons. These force sensors are reading exactly what they should read. There is, in this case here, a force down, 9.8 newtons, and there is a force up, 9.8 newtons. This is an equilibrium. The forces are canceling out. If the force that this was pulling down with was greater than the force that the string could provide, the string would break and this would start to accelerate downward. It would be on balance. Likewise, if I were to grab hold of this force sensor and yank it up in the air, I'd be providing a force greater than 9.8 newtons, and that would cause the object to accelerate upward. In both of those cases, the string breaking and me yanking it up, that is an unbalanced force. Right now, everything is balanced. It's at rest. There's no acceleration. The net acceleration is zero, so the object is not displacing itself. There is no force, no extra force down. There is no extra force up. Everything is in balance. When I take this string and I attach it to both sides of this apparatus and look at the force sensors, I see that the force sensors do read zero. And again, I've tared it just to make sure that we're going to get the best data and nothing is disturbing our measurements. So I'm going to place this mass in the middle. Now, if we had two strings, these two force sensors are right above each other, and I hung this mass on it, we would say that one string would pull up with 4.9 newtons and the other string would pull up with 4.9 newtons. They would be both holding half the weight. But in this case, they aren't right above the weights. One force sensor is over here, the other one is over here. And so when I hang this in the middle, do these read 4.9 newtons? Let's find out. As we can see on the screen, they do not equal 4.9 newtons. In fact, this 9.8 Newton force has on it a force of approximately 19.6 newtons upward. But it's not all up. Some of it is in the x direction. And you say, well, where did that extra force come from? Because we only have 9.8 newtons pulling down. But when I take this string and I let it down, we again can see that it goes back to reading 9.8 newtons. But when I start pulling it to the side, the force starts to go up. Why is that? Well, the force is going up because as I start pulling this to the side, there becomes a greater and greater and greater X force. And so there's a force that's going in this direction that is going to be, now you can see it here, I'm going to hold this right alongside, I'm balancing it, I'm holding it, and as soon as I start pulling it over, we're seeing this force increase. And the answer to that is because now the force sensor and the rod that the force sensor is attached to and the desk that the force sensor the rods are attached to, Newton's third law, is going to have to pull this in this direction, pull the mass in that direction. If I let go of this, I'm not going to do this because it could break this, but it will swing down to the side. You can see the pendulum type action there. And so there is going to be a tension on this string, a force on this string to support it vertically, but also to keep it balanced left and right. And so when we do our mathematics on this, we find that there is that additional X component that wasn't in the mass gravity relationship, the original weight relationship, that has been created because we've pulled the mass sideways. Now, we can do some calculations on this. This is not a perfect center. When we measure the angles here, we find that one side is about 33 degrees and the other side is about 30 degrees. Close, but not exactly the same. That's why we have a little bit of difference here in our calculation, calculated force, measured force on the screen. If I were to move this weight over to one side, what do you think will happen? If you said that the force sensors would read different values, you'd be correct. And the reason that is because in this particular case, this force sensor over here is supporting more of the weight than over here. But this force, this string has to still pull across. And so even though this is supporting almost 9.8, there is still some horizontal force created. That also means that there has to be a little bit of horizontal force here as well. And so the sum of these forces still is not 9.8, it's much larger. It looks on the screen to be about 12.9. And so this force and this force don't balance out to 9.8, but they balance out in terms of the y's. The force that this is pulling down with, this weight, is 9.8 newtons. The y component here plus the y component here add up to 9.8. And then we have the newly created x components. The angles on this equate out to, and we're going to do some measurement on this. I'm using a protractor. So the angles on this equate out to about 65 degrees and about 15 degrees. So we have a 65-degree angle in here and a 15-degree angle in here. From your perspective, this is 65 degrees, and in polar coordinates, this here would be 165 degrees. What I want you to do is calculate if these forces that are on your screen are correct. We know that this is 9.8 newtons at 270 degrees. We know that this angle is approximately 65 degrees. We know that this angle is approximately 165 degrees. We know that there is a tension on each side here. Solve for it. Do the algebra using your vector addition table to solve for that tension. Once you've done that, then compare those values using percent errors to the values on your screen. I'm going to tell you, you're going to have error. there's a couple reasons you're going to have error. One, these force sensors do have a little bit of error in them in terms of them becoming a little off by a tenth or two in terms of holding their zero value. So this could be off by a tenth or two in terms of force. You can see it jump around a little bit. The second reason it could be off is because I've just used a protractor to measure the angles of these strings, and I am only giving you the value to within 5 degrees of precision. When I take a look at it, the protractor does move a little bit. Where these strings actually meet, there's a knot here, is off a little bit. So we know that it's about 65 and about 165, but the exact angle, we have not measured to that level of precision. So you might get some values a little bit off of this. If you get 5 or 10% error, I wouldn't be too concerned. I think what's more important when we look at the answers is that, one, you can calculate them correctly, and two, that you observe that the tensions are different in this case, that the Y components add up to the 9.8 newtons down created by this weight, and that there's now this new X component that came because it's getting pulled to the side. If I take this weight and move it over here, this is going to give me yet a third angle, and we will see the similar result. This force sensor on this side holds a greater amount of force than the force sensor located on the other side. And as we are doing our measurements, we will see that that matches the concept we had over here. That when the angle was steeper, and the angle is going to be steeper here than it is here, we take our protractor and we measure it, and we find that the angle on this side is approximately 40 degrees, and the angle on this side is 25 degrees. So we have a 25-degree angle, we have a 40-degree angle. So there's a greater angle here, and because of that, this force sensor is going to be taking a greater amount of the Y force. The X forces here will be the same. The X force on this side, the X force on this side, they have to be equal and opposite. This one carries a little less Y than this one in this case. The steeper the angle, the greater the Y force. And so it is, this force sensor on this side now carries more force than the force sensor on this side. Again, what I'd like you to do is go back and, using the data that we see on our screen here and the angles that I have provided, that we go back and we calculate precisely the values of the tensions, and then we compare those using percent errors. If you have any questions, please let me know. Have a great day.